In this lecture, we will discuss about Dirac delta function. To understand the concept of Dirac delta function, suppose there is a screw and we apply a large amount of force on that by hammer. But the condition is that this large amount of force will be applied for a very short interval of time. So the function that is needed to represent such a large amount of force for very short interval of time is a function called Dirac delta function, and it is represented by such a graph where you can see that in the beginning, when there is no force, it is 0 up to this point. Once we reach at this point, we get a very large spike, and this is because at this point we apply a large amount of force on screw for very short interval of time. After this spike, we get a 0 again. Hence, we can define now the Dirac delta function, which is represented by delta of x, that it can be pictured as infinitely high, infinitesimally narrow spike with area 1. And that you can see in this graph, where the first infinitely high, second infinitesimally narrow spike, third this spike should be of area 1. Hence, delta of x is only defined at x is equal to 0, and that is infinite, and elsewhere it is 0. And we can take the area of this Dirac delta function, and that is from minus infinite up to plus infinite of delta of x dx is equal to 1. Hence, there are these two conditions for Dirac delta functions. These two expressions show that Dirac delta function is a singular function that vanishes everywhere but only defined at x is equal to 0. Technically, delta of x is not a function at all, but it is like a distribution that spikes off to infinity at x is equal to 0, and it is 0 elsewhere. Hence, by taking the integration from minus infinite to plus infinite of this Dirac delta, we get a 1. Hence, based on these conditions, it is identified as a generalized function or distribution. Now, assume that instead of a curve, it supposed to behave like a rectangle where it has a height n and width 1 over n. If you multiply height with width, you get 1. So it means the condition of having the unit area is fulfilled. Even if you take this rectangle or this rectangle, you get 1. Next, please note that Dirac delta function doesn't appear alone, but it always appears with some function. Suppose f of x. This function could be a linear function, quadratic, sinusoidal function, or exponential. But the combination of delta of x with f of x is 0 everywhere except at x is equal to 0. So because it is only defined at x is equal to 0, hence we can write f of x delta of x is equal to f of 0 delta of x. Because again, f of x is 0 everywhere except at x is equal to 0. So it means it is only defined at f of 0. Hence, we can write f of x delta of x is equal to f of 0 delta of x. Now, the area of this function would be like minus infinite up to infinite of f of x delta of x dx is equal f of 0 integration on delta of x dx, which is nothing but 1. So we simply put the 1 for this expression and we get f of 0. Next, please note that it is not necessary that the integration would be from minus infinite up to plus infinite, but it could be also some finite limit. For example, from minus epsilon to plus epsilon. This epsilon could be any number, 5, 6, 7, or any number. Another important definition, please, you should always remember, and that is we can shift this spike from 0 to some other point. For example, if we want to shift this spike from x is equal to 0 up to x is equal to a, then simply the delta function will be like delta of x minus a, which means that at x is equal to a now it is defined, but elsewhere it is 0. Now, by taking the integration from minus infinite up to infinite of this term delta of x minus a dx, that would be equal to 1. It means the area should be still 1. Now, if you just follow this definition where we mentioned that delta of x doesn't appear alone, so by keeping f of x with delta of x minus a now, because we already mentioned here that this is only possibly defined at x is equal to a, so hence we can say that f of x delta of x minus a is equal to f of a delta of x minus a. And we can take the area of this function, and that is minus infinite up to infinite of f of x delta of x minus a and to dx, that would be f of a. Let's have a look these two examples based on these definitions. For example, the first one, integration from minus 4 up to 2 of delta of x plus 3 into dx. Please, if you simply take x plus 3 is equal to 0, then you have x is equal to minus 3. Now to find either this the spike of this function lies in the limit of this integration or not. So having checked that x plus 3 is equal to 0, where x is equal to minus 3, hence the peak is at minus 3. So we simply say that now if this minus 3 lies in between minus 4 up to 2, then we will say function exists and peak lies in the limit. And that is exactly happening here, where from limit minus 4 up to 2, minus 3 lies in between this limit. Hence, we can say function exists and peak lies in the limit. Let's have a look at this example where x minus 2 is equal to 0 and we get x is equal to 2. If you look the limit of this integration, that is from minus 2 up to 1. So it means that 2 doesn't lie in the limit. Hence, we can say about this function that this function doesn't exist and peak is out of the limit. Dear students, that's all for the today's lecture. Please subscribe to my channel and share this video